right, well, let's get started today. Okay. For this week, we have quite a few things to talk about. I'll probably only get through my track record if anything to go by, probably the first little half of this. But let's try to do it well, and then hopefully the rest of it will make more sense. Okay, so here we are talking about interference today. And or this week, we are going to discuss interference. And to do that, I'll just recall a lecture way back week 2, where we saw the sum of two waves with slightly different amplitudes and phase difference here. 1 radian, we discussed how you just add up the two waves at each location. And from that, we saw that when both waves have, like, say, some phase difference of 0, then the maxima coincide. So build up to a bigger maxima, and also the even the negative maxima, and of course the minima are also coincident, 0. But then as soon as you start introducing some phase difference, now the wave changes. The output wave is no longer the same. And in fact, there is one situation where when the phase difference is exactly pi, you're going to get nearly destructive interference, and the resulting wave is like has a very small amplitude, and the only reason it's not 0 is that the two amplitudes are not quite equal to each other. And here, the maxima coincide with the minima of the other wave. So the gray dash line, the gray solid line, and the dash line are the two individual waves, and we saw this behavior. Okay. So again, if you recall, I said to you, you should always know phase difference of pi, 3 pi, etc. All of these are going to result in destructive interference. Constructive interference is when they are in phase, which is phase difference of 0, 2 pi, 4 pi, etc. So from that, actually, we supposed to be a well, okay, it's all right. I'll just read out the words. I was going to go through them one by one, but the point is, this is something we've already introduced, which is the Poynting vector, or the irradiance intensity, which we said is proportional to the time average modulus squared of the electric field. Okay, and most detectors can only detect this time average Poynting vector, not the direct electric field itself, all of the usual detectors that we use for optical frequencies. And at lower frequencies for sound or RF microwave, it's possible to actually follow the field, like to follow the individual variations of the field, the electric field itself, rather than the intensity. And also, conversely, by observing on even shorter time scales with lasers, so now this year's Nobel Prize was given for attosecond laser development. So the Nobel Prize is for the development of like ultra short laser pulses, where the pulses are now of a time where individual cycles of the optical field become visible. Okay, and by using such laser pulses, we can actually follow the development of optical fields as well. Okay, now, and they can like resolve, of course, much shorter events like electrons orbiting around the atom and so on. Anyway, so that's this year's Nobel Prize. So and so that's a very interesting topic. But for our consideration here, we are going to look at now two fields, and we're going to consider obviously the sum of the two fields and calculate the intensity, the irradiance from the sum of these two fields. Okay, because so far we were just talking about the addition of the fields. Now we want to look at the sum of the fields, and we want to consider a very general situation. We have linearly polarized monochromatic waves of the same frequency. So omega is the same for both. We'll see what will happen if I relax this requirement. We also might have a phase difference, epsilon1 and epsilon2. So initial phase, epsilon1, initial phase, epsilon2 for these two waves. Okay. But what is different is that the two waves are coming from two sources. And so the physical picture in your mind is picture two sources that are emitting waves. And we are looking in some direction, which is, which gives us the K1 at a point P. So we have two sources, and then we have some point P over here. And so the direction of the wavefront from source 1 to that is K1. Direction of source 2 to that point P is K2. The position of the point P is at the coordinate R. Okay. And these are the individual electric fields of the 2 points. And we'll also have 2 other sort of not requirements, but it'll help us to approximate the answers a little better. Is we'll assume that the separation between the sources is much greater than a wavelength, and we'll also assume the point P is much greater, further away than is far enough away that these wavefronts can be just written in this planar wavefront form. Okay, so we don't have to worry about the spherical sort of nature of the wavefront. Okay, so that's our situation. So now let's look at what happens to the overall electric field. Okay, so we know the intensity is just given by the time average of E squared, modulus the magnitude squared. And sometimes I'll write the magnitude, sometimes I'll forget. So just assume that's always the magnitude squared. And the total field E is, of course, the sum of the 2 fields, E1 plus E2. And so then when we want to consider E squared, we just take E1 plus E2 dot product with E1 plus E2. Okay, so that's E1 dot E1, which I write as E1 squared, E2 dot E2, which is E2 squared, and then of course 2 E1 dot E2. Okay. Now, if I take the time average of each of these terms, because the time average is just an integral, which is a linear operation. So time average of E1 squared will give me I1, time average of E2 squared will give me I2, and then we have this dot product, E1 dot E2, the time average of that. That's the term that we call the interference term, because it's appearing because of the fact that the 2 waves are interfering with each other. This extra term appears. And now we'll consider what happens to this interference term, and everything we talk about in this part of this week, this lecture and next lecture is all about what's going on with this interference term and how in different situations what this interference term looks like. Okay. So again, yeah, I1, I2 come from the first 2 terms, and the third term then is the time average of E1 dot E2. So that's what we're going to look at now. Okay, so substitute the plane wave form for the fields and expand and use the cos squared omega t. So I claim that this is the answer, and I will show you that now. Okay. R12 is equal to 2 times the time average of E1 dot E2 over here. And each of these terms is identical to the other. It's just E01. I mean, they look the same. They're not identical, but they look very similar to each other. Just with the 1 replaced by 2. Okay, so we have to take that dot product and we have to calculate the time average of it. Okay, so to do that, we will write E1 dot E2 first. Okay, that's going to give me this E01 dot E02. So there's the vector nature of the fields comes in right over here. So you should immediately see from this, if E01 is horizontal polarized and E02 is vertical polarized, what will happen to the dot product? 0. Exactly. So if the 2 polarizations are orthogonal to each other, and the easiest case to see is linear orthogonal polarized, right? Horizontal and vertical is obviously going to vanish because they're along X and Y directions. But you can also show this, it turns out, for other states of light. So for example, right circular and left circular will also give you zero. That's a little bit harder to show. In fact, it'll be easier to show with phasors, something that I'll talk about later in this lecture. Okay, but for now, it's hopefully clear to you that orthogonal polarizations vanish. That is, the interference term vanishes, and only the same polarization states will give you interference. Okay. So now we have these two terms, so we'll write them out. And we have to take the time average, which obviously the time average is of this whole term over here. So to do that, we expand out the terms. So we're going to get cosine k1 dot r minus epsilon 1. I'm just treating the term that I'm caring about the most is the time varying component. So I'm going to expand the cosine and I'm going to use the formulas, which I'll just write it over here. Cosine a minus b is equal to cos a cos b plus sine a sine b. Okay. So the minus, this is the b that I'm talking about, and k1 dot r plus epsilon 1 is the a. Okay. So you can see there are many terms here because each of these has to be written out as cosine k1 dot r cos omega t plus sine k1 dot r minus epsilon 1 sine omega t. Okay, that's the first term. And then I multiply that by exact same thing with like 1 goes to 2. Right? It's just the same term, just multiplying it out. That will have the same thing, just the ones replaced by 2. Okay, I'm not writing out every term. So when you now multiply these two together, okay, let's look at one of these terms. So you'll get a cosine omega t here, and there's a cosine omega t over here. That will give me cos k1 dot r minus omega t, minus epsilon 1 times cosine k2 dot r minus epsilon 1 times cos squared omega t. Remember, I had to take the time average. That gives me time average of this guy. Okay. Is that clear to everyone, this step? How I got here? This is one of the terms in that when I expand out, there'll be 4 such terms, right? So there'll be cos k1 dot r times its equivalent, and then I can also write, the sine terms. This will be another term plus sine k1 dot r minus epsilon 1 sine k2 dot r minus epsilon 2. Epsilon 2 times sine squared omega t. Again, time average, and then you can see there will be terms which go as cosine times sine with 1 replaced by 2 times cos omega t sine omega t, and then similarly sine omega t cosine omega t. 1 and 2. Do you need me to write out every term? Would you prefer? I can do it. Does everyone prefer me to write out every single term here? Not seeing any. You don't maybe care. But let me write it. Okay, so, all right, it's a lot of terms, but they hopefully make sense. And what we need to remind ourselves is the time average of cos squared omega t is 1/2. So this part is 1/2. This part is 1/2. I showed you this in a couple lectures ago, but you can also verify it for yourself. Just take the integral of cos squared omega t over one time period. Because remember, t is always some large number, which you can take to be integer number of time periods. So, or n times 2 pi over omega. So doing it for just one time period is equivalent to doing it for n such time periods. Okay. So each of these will give me half, and then these will vanish. Okay. The sine and cosine terms, cosine and sine terms, whichever way you want to multiply them together, those vanish. So these terms go away, and I'm left with now cosine k1 dot r minus epsilon 1 cosine k2 dot r minus epsilon 2 plus sine k1 dot r minus epsilon 1 sine k2 dot r epsilon 2. Okay. Okay, I see. Sorry, I made a mistake. This should have been plus all along. Nobody told me that. All of these were always plus because that's what I started with. All of these minus signs there. Okay. Yes.
So where did the 1/2?
Oh yeah, well, there's 1/2. Oh. Okay. So this, of course, this cosine cos A cos B sine A sine B, again using the same formula. This is just 1/2 cosine a term which I'm going to call delta. Okay, where delta now is just this guy minus that. Okay, so it's k1 dot r plus epsilon 1 minus k2 dot r plus epsilon 2. So that can be written as k1 dot r minus k2 dot r plus epsilon 1 minus epsilon 2. Okay. So and remember also this this I12 had a 2 in front of it. So those two cancel each other. So when I write down the term, you'll see that. Everybody okay with this derivation? Any questions? It's important to see the general derivation once so that you know from now on. I'll just keep using this without re-deriving it for every single situation. And so that is our formula. So the 1/2 and the 2 cancelled out from that earlier derivation because there was 1/2 from the cos squared, and then there was a 2 from the 2 E1 dot E2. So we got E01 dot E02 cosine delta, but delta is exactly that formula that I just derived on the board. Okay. And again, if the fields are orthogonal polarized, the interference term vanishes. Now we can simplify this a little bit further. If the fields are in the same polarization state, so this E01 and E02 are along the same direction, then this becomes E01 times E02, and this becomes cosine of delta. Then we can now use the fact that I1, the intensity, is simply E1 squared time average. So that's just E01 squared over 2, just amplitude squared divided by 2. Okay. And similarly, I2 is also E02 squared by 2. Proportional. There's of course, there are some extra terms with C and epsilon naught, but those are assumed to be the same for both. So we have that I2 is E02 squared by 2. So I substitute for E02 as square root of 2I2, E01 as square root of 2I1. So up here, this is square root of 2I1, square root of 2I2. So the overall term is 2 times square root I1, I2 cosine delta. That's the interference term. And remember the other two terms from E1 squared and E2 squared gave me I1 and I2. Okay. So this is our final expression for the for the overall interference pattern. I equals, this is a very important and famous relationship, which you should probably try to remember. That is, I is equal to the sum of the individual intensities, which is what you would expect. If you take two waves, or you take two sounds, whatever it is, and you put the energy from the two waves, at a point, you would say that the total energy, which is, remember that irradiance is just energy per unit time per unit area. So imagine that you have a detector which is looking at some incoming waves or incoming sound or light or whatever it is. If you were asked to predict what would be the total energy that this detector would register, you would say is the sum of the energies, right? But what we are saying is actually it's a little different than that. It's the sum of the two intensities plus a term that varies across the detector, across the area of the detector. Because as you know, delta depends on K1.R minus K2.R. That is, it varies with the position on the detector. So sometimes it can be more than the sum of the two energies. Sometimes it can be less than the sum of the two energies, depending on exactly where I am on the detector. So that is also shown here. And I don't know why none of my animations are working. It's really frustrating. I'll just keep going. All right, so from that expression on the earlier slide, this one over here, you can see when delta equals 0 or 2 pi, 4 pi, plus or minus, it doesn't matter. This cosine delta will be 1. Okay, and when delta is pi, plus or minus 3 pi, odd multiples of pi. So even multiples of pi will be constructive interference. Odd multiples of pi for delta will be destructive interference. And that is shown here. So constructive interference is when delta is even multiples of pi, and odd multiples of pi give me destructive or interference or minima. And you can see the two intensities. The maxima are I1 plus I2 plus 2 square root I1 I2. I minimum is I1 plus I2 minus 2 square root I1 I2. As you might expect, if I add up the two and take the average, I get I1 plus I2. So on average, the energy is simply the sum of the energies. But depending on my position on the detector, I can sometimes see more or sometimes see less. Okay. And now let's take the extreme case where the two waves have exactly the same intensity. I1 equals I2 equals I0. So I substitute that in here. I get 2 I0 times 1 plus cosine delta. Okay, and this is often what we'll approximate most sources to be. We'll say that we roughly equally split the wave or the amplitude in half. So I1 will always be I2. So this is the simplified expression, which will often be the one that you see in your experiments and in the theory, in the problems, etc. that we do. Okay. So this distribution is called the cosine squared distribution, clearly, because 1 plus cosine delta is cos squared delta over 2, 2 times cos squared delta over 2. Therefore, we also can now again put, for delta. And so one thing I should mention is we have this delta over 2. In some books, you'll see this as the phase difference. So they'll say that the phase difference is 4 I0 cos squared delta. Where by delta, though, here they mean half of what we are calling delta. Okay, so it's just, you have to watch out for those little factors of 2, depending on the notation that people have put into their textbooks or etc. So if you're looking at any other textbook, but if you just follow Heck, then this should be hopefully consistent across the board. And yeah, so then we get the minimum intensity is 0, because when delta equals pi, cos delta over 2 goes to 0. And when delta equals 2 pi, cosine delta is equal to minus 1, but here is a square, so it doesn't matter. So we get I max equals 4 I0, or of course, when delta equals 0, again, cos delta equals 1. And therefore, we get 4 times I0. So those are the two extremes. So you'll get a pattern. Thought I had a graph of this pattern. Maybe it'll come out in a minute. Sorry. So the pattern looks like a cosine squared. In case you graph that, I'll show it to you in a minute or so. It's always is above 0, obviously, because it's a square of the cosine, and its maximum value is always going to approach, is again going to be 1. So that's when this maximum value becomes 4 I naught, and the minimum value has to be 0. That's when, so it'll look like that. Okay. And now we can make a further approximation. Remember that K1 and K2 that we were taking to that point P, we were assuming that, they could be different in the magnitude as well as in the direction of this K1 and K2, for example. But now, if we assume that the source separation is small compared to the location of the sources, right? Like meaning the points where we are looking at the interference, we may consider the amplitude to be independent of the position, meaning that we're just assuming that the amplitude at the location of the detector is independent of how far away I move the detector in space, basically. So what I mean is, I don't want to pull everything up and go through that. I'll just try to sketch it over here. Side. So I have the two sources which are separated by a distance A, and then I may have 2 points P1 and P2, and they are at, let's say P1 is over here, P2, let's say, is a little further back. Okay, so this is R1, the distance, and then R2, the other distance. Well, this R1 minus R2 is much greater than A and also the wavelength. Okay, and we're also assuming A is greater than the wavelength. Okay, it's on the order of, but it can be considered bigger than the wavelength. So because of this fact, we can just ignore the change in the amplitude. We don't have to worry about the amplitude itself. We just look at this K R1 minus R2 plus epsilon 1 minus epsilon 2, and we get this expression for the cosine squared distribution. So that is, man, it's all this beautifully animated. It always shows up in one. I understand why. Okay. It was working this morning. Okay. I don't know why it's not working. That's annoying. All right. I apologize that it looks so busy. If it had popped up one by one, it wouldn't look quite as busy as we were watching it. And it was working this morning when I played through the slides. So I don't know what's happened to this presentation. I'll probably have to restart PowerPoint. I don't want to go through that. Okay, so here are my sources S1 and S2. Okay, here's the point of observation P. Okay, so this is R1 and R2. Okay, so instead of looking at K1 and K2, I made the position S1 to P as R1 and the position from S2 to P as R2. And so that gives me the phase difference between them, which is that R1 minus R2. And or from the previous slide over here, the phase difference is K times R1 minus R2 plus epsilon 1 minus epsilon 2. Okay. So for a minute, assume that epsilon 1 minus epsilon 2 is 0. Okay, just ignore that part. Okay. Then if I look at this expression here, when R1, remember when the phase difference was a even multiple of pi, I got constructive interference. Odd multiples of pi gave me destructive interference. So even multiples of pi are 2 pi m. Okay. And now I just bring that K down here. So it's K times R1 minus R2 is 2 pi m. So which is then giving me R1 minus R2 is 2 pi m divided by K. And K, what is K? In terms of some other quantity. You know, remember what K is? Yes, Paul.
It's like 2 pi over lambda.
Exactly. So K is 2 pi over the wavelength. Okay. So when I put that in here, 2 pi's cancel out and I get m times the wavelength. So when the difference between the distances R1 minus R2 is m times lambda, okay, just from this expression, we are going to get constructive interference or maxima. those are called fringe maxima, and they are hyperboloids. That's because you may remember an ellipse is constructed by taking the sum of the distances between 2 points, which are called the foci, and making that a constant. When you take the difference between the distances from 2 points and make that a constant, you get hyperbolas. And in 3 dimensions, a hyperbola will become a hyperboloid, which is a figure of revolution around the central axis between the points S1 and S2, the 2 sources. Okay, so that's where we are getting these hyperboloids from. So we can have, of course, m can be any integer. So m equal to 0. When m equal to 0, the points that are in this plane, which are exactly equidistant from S1 and S2, right? That's the plane that cuts the line between S1 and S2, is the bisector. And that whole plane is called the 0th order fringe. That's again because the order is 0. When m equal to 0, order is 0, and that means that also all the points there are equidistant from S1 and S2. That's the first, and then the first order is clearly when m equal to 1. So that means R1 minus R2 is equal to 1 wave lambda, right? M equal to 1. Or m equal to minus 1. Again, it doesn't matter for this whether it's plus or minus 1. Those are both called the first order maximum. Okay? And there are going to be 2 of them, one on either side of the 0th order fringe or 0th order maxima. And yeah, so that's pretty much the most important thing to note here. And then, of course, in our actual detectors or in our actual experiments, we're not observing the entire hyperboloid surface. We're typically locating a screen or a detector at some location in a plane. And so here, for example, I've drawn a plane that encloses all 3 points, S1, P, and S2. Okay. Right now, this plane also includes the axis between S1 and S2. But you could also imagine taking that plane and just including, say, the point P and cutting through the hyperboloids. That's the fringes that you're actually going to see. So in practice, what you'll be seeing is a cut, a cross section through the hyperboloids, depending on where in space you're observing it. And you can see that, if you're right in this plane, you will get hyperbolas. But close to the center, you're going to see nearly straight line fringes. Okay. And of course, as you get further closer to S1 and S2, you may start to observe this curvature of the fringe. Similarly, if P is located not in the plane containing S1 and S2, but somewhere much further out, now you've got these hyperbolas, they're starting to look almost planar. As you go further and further away, the curvature of the hyperbolas falls off, right? Because it's just a curve that's like, further and further out, it's going to look more and more planar. And at that point, when I take a cross section through those hyperboloids, I'm mostly just going to see lines. Okay, and those will be the fringes that we observe in most experiments, like say Young's double slit and other experiments. We'll come back to other types of fringe patterns that we might see. Also, I should point out the fringe minima. Okay, so we talked about fringe maxima. Fringe minima will be just this R1 minus R2 now is an odd multiple of pi, right? So this m prime is always an odd number over here. And again, I guess I should have noted here, m prime is an odd number. Okay, so that's important to remember. And that minima is pointed out here that falls in between the 2 maxima. So there's like a pattern which is like 0th order maxima, then a minima, then the first order maxima, then a minima, and so on and so forth. Second order, third order, etc.
So if you just take the continuum, is this just a physical interpretation of the path integral in quantum mechanics?
The what?
The path, summing over the path, the path integral in quantum mechanics.
Is this equivalent to that? I don't think so. Maybe. I guess, if you looked at all of the paths that the waves, the photons could take, then maybe. I'm not sure. I'm not sure that's equivalent.
In computing the intensity, so from the continuum of the paths.
Yeah. I don't think so, but I could be wrong. I don't know the answer. Yeah, let me say that. Okay, so So in the far field, which is when R1 and R2 are much greater than the wavelength, and this is that cosine squared distribution I was just telling you about. This is the distribution when I look at it in the plane, in that plane that I was cutting through. This is the pattern of the intensity. Okay, it's going to look like a cosine, but it's really a cosine squared. And what you'll see on your screen will be like a bright spot and then a minimum, another bright spot and a minimum, etc., etc. Okay. And so what we call the far field distribution for interference pattern is this situation that I was just telling you. R1 and R2 are much greater than wavelength and also greater than the separation between the sources, S1 and S2. Okay. So the amplitudes, as I mentioned, for the two sources is going to be very similar at the observation point, nearly equal, basically, and only the phase difference matters. The phase difference, as we saw, is governed by, whether one wave has advanced a little bit a wavelength more than the other wave, or so that the two waves overlap, or it has advanced only half a wavelength more, and in which case the maxima and the minima will overlap, and then you'll get destructive interference. Okay. So again, that's another physical way to think about this earlier expression here. So when R1 minus R2 is m times lambda, it's as if I were to think about it in space, that one of the waves has advanced an extra wavelength, but that still brings me back to a maxima and a maxima overlapping on each other, so I get constructive interference. Whereas when this m prime, which is an odd number, if I go to a minimum, then what has happened there is that one wave has advanced only by lambda over 2. Okay, and the other wave is, let's say one wave is at a peak, and the other wave has advanced by lambda over 2 because of the phase difference, the path difference, the path difference is exactly lambda over 2 different for one wave versus the other. So that lambda over 2 means now a minimum or a negative maximum coincides with the plus maximum. Therefore, the two will destructively interfere. Okay, so that's why, again, that's another helpful maybe way to think about these path differences. Instead of remembering this is like that, when you have an extra wavelength, then the constructive interference takes place. That is, the maxima will overlap. And when the path difference is lambda over 2 or odd multiples of lambda over 2, then you're going to get a negative maxima and positive maxima coinciding, and that will give you a destructive interference. Okay, so what I call the far field, basically the pattern always looks like this. There's no change in the pattern, just the spacing between the fringes might vary. As I go further and further out, the spacing between the fringes will go further and further apart, just because of the way those hyperboloids are spaced out, right? But the pattern itself just remains the same. Okay, there's no change in the pattern. Okay, but in the opposite regime, which we'll rarely see, but might occur in some experiments, for example, Fresnel diffraction, as we'll see later, is that the pattern itself changes its nature, its behavior, as we go from one distance to another distance. So here, for example, S1 and S2 are over here, and I'm looking very close to the slits, okay, or very close to the sources. In that case, you get this one pattern. There's some fringes. I think this was drawn for the phase difference, path difference of 2 lambda. And then you go to like 4 lambda. Now suddenly the pattern looks quite different, right? You see that there are like this many fringes, but then there's this extra little tail out here, which is different, and there's a peak over there. So it just changes its the very type of pattern that you see is now different, and that's going to vary. That's because we are in what's called the near field, okay, where R1 and R2, the distance, are on the order of the wavelength, and A are also comparable to the slit distance or the source. So now the phase and amplitude can both change. That's the problem, right? The amplitude is not just fixed, but it can actually change across the region where we're looking at the interference. Okay, so that kind of concludes some very general considerations of interference. Now we want to specialize. We want to go to very special cases of interference where we are looking at like different setups where we create interference patterns. Okay, and but now that we have the general consideration, we'll just take that general consideration and apply it to the different special situations like Young's double slit and Michelson and thin films and all this stuff. But before I do, I want to talk a little bit about a mathematical technique, or really a geometrical technique that we'll often use, which is called phasors. And the reason we introduce these phasors is that, we've been adding up these two waves, like you just saw, that cosine of one wave plus cosine of another wave. Well, as we look at more and more difficult problems in interference, we're going to be adding more than two waves together. Okay. So the earlier consideration I did for you works for like two waves. I can calculate all the trigonometric identities, but you saw it has quite a bit of algebra as well. But as we'll go forward, we'll be considering sums of like 2 waves, 3 waves, 4 waves, hundreds of waves, maybe infinite number of waves. Okay. And now it's going to be very difficult to keep track of all these cosines in all these situations. So we're going to use phasors, which is complex numbers, to keep track of these interference or these sums and so on. Okay. And the reason, okay, so what is a phasor? Well, it's really just a complex number, but in a particular way that we are interested in, that I'll introduce now. So you all remember complex numbers, I'm sure. So we introduce x plus iy, the imaginary axis. And so here we have a point in this complex plane, which is x plus iy. And we can also draw an arrow which represents the phasor. Okay, the phasor is just that arrow that we draw from the origin to the point x comma y in the complex plane, which is also now this complex number x plus iy. Okay, and also we have the polar form representation for that complex number. Sometimes you might see a tilde above the z, which just means it's a complex number. It's a phasor, not just a real number. Okay, so because sometimes we use x, y, z to represent 3 dimensions, but then I'll also use z to represent complex numbers, so it can get a little confusing. So to differentiate, I might put a tilde on top, or sometimes I'll just assume from context what it is. Okay. So now the polar form for that same complex number is just taking the angle theta over here, and so r cosine and the magnitude r. So r cosine theta is x, r sine theta is y. So we can write r cosine theta plus I times r sine theta. And then the complex conjugate of z is just taken by flipping the imaginary part down to minus y. So the same x plus iy becomes x minus iy. And you can see that's just rotated down clockwise from the x-axis by theta, the same angle theta. Okay. And why this is helpful is, as we have seen, a lot of our waves that we look at in the interference and many of the considerations, we always have this time and spatial dependence. So kz minus omega t is in there. For just omega t itself, we can already see that this is a helpful visualization of what's going on. As time goes on, that angle theta grows as omega t linearly with the time. Okay. And similarly with z, we can also, if we freeze the time and look at the z, then it will grow linearly with z. Okay. So let's look at this. So yeah, I've already talked about all this. But the most important thing to note is that the phasor by itself does not have a real physical interpretation. Okay. It's a mathematical extension, if you like, of our regular real wave. And when we want to calculate actual physical quantities, like when I want to calculate what the intensity is or what the actual value of the electric field is, I had to take the real part of this phasor, real part of this complex number. And usually we'll always take the real part. You could also take the imaginary part if you wanted, but the convention is always to take the real part of that phasor to find the physical wave, the physical amplitude. So let me just also put in some important phasor facts. We'll use this often. So you remember the z star, which was the complex conjugate. I wrote it as e to the r e to the I theta, right? Because we can use the Euler formula for just z. Z is equal to r e to the I theta, because r cosine theta is the x component, r sine theta is the y component. So r times cosine theta plus I sine theta. This cos theta plus I sine theta is represented as an exponential. This actually is where a lot of the mathematical power comes from, because we can start using the easy way of manipulating exponentials rather than trigonometric functions. And this is the Euler formula. Now you can see for z star, I've just flipped the sign of the y component. So this gives me a minus sign, and that becomes r e to the minus I theta. Okay. So that's shown over here. This is x minus iy, it's r e to the minus I theta. And then whenever I want to find the real part of a complex number, all I do is take the complex number plus its complex conjugate and divide by 2. Okay. So that's an easy way to find it. If you have, say, the polar form, to go to the real part, I just take z plus z star divided by 2. Similarly, imaginary part is, oh, there's a mistake. Z minus z star by 2i. Sorry, okay, there should be a 2i for it. So, and then the magnitude r is simply taken by multiplying the real and the imaginary parts and taking the square root. A lot of cases, like in intensity or irradiance, we are interested in the magnitude square. That's the intensity. So we'll just take z and multiply it by z star. A couple other facts here, it's easy to verify. But then probably the more important thing to note is that whenever I take two phasors, say, and I suppose I multiply a phasor z by e to the I2 pi, that's like making the phasor rotate by an angle 2 pi, right? Because if z is equal to r e to the I theta, then multiplying by e to the I2 pi is like adding 2 pi to the angle, okay? And since e to the I2 pi is equal to 1, we see that we come back to the same phasor. Similarly, if I take the phasor z, r e to the I theta, and multiply by e to the I pi, okay? Now e to the I pi, if you calculate what it is just minus 1. But also you can see the same thing is happening. I'm rotating the angle now by pi. So I'm flipping the angle by pi, that's equivalent to multiplying it by minus 1. So if I take the same phasor that's at an angle theta, and I rotate it by pi 180 degrees, that's equivalent to multiplying the phasor by minus 1. Okay. And also pi over 2, that's a rotation by an angle 90 degrees, that's equivalent to multiplying it by plus I. Okay. Or minus I if it's minus I pi over. Okay, so the addition rule for phasors is the same as vectors. So for example, this is from one of the lecture 2 where we did the full calculation for taking cosine omega t and cosine omega t plus pi over 3 and adding it. Okay, we did the addition by using trigonometric functions, but now we're going to do it either using simple vector addition, like you all know this parallelogram law for like adding vectors. So we can take, the vector z1, which represents cosine omega t, and the vector z2, which is now the phasor for the cosine omega t plus pi over 3. The angle between them is 60 degrees, pi over 3. Then the sum is just taken by using the usual parallelogram addition. Okay. And this just represents that the projection of z2 on the x-axis is just that real part, which is this. The real part of this is cosine omega t plus pi over 3. Okay, and of course the original one, e to the a cosine omega t, is just along the x-axis, and both of them will rotate together at the same rate omega t around this x-axis. Okay, so we can just freeze them in time at any given time in this orientation and add them up together. So now, if I want to add up the two phasors or add up the two waves, what I'll do is very simple. I'll add the two phasors z1 plus z2 and take the real part. Okay. That will give me the equivalent of taking psi1 plus psi2 and doing it by using cosine and sine identities. So it's very straightforward. Here, this is just, again, as I said, the e to the I omega t sort of factors out because each of these goes as e to the I omega t. So I can just take that out of this addition. And I just need to add these two together. So to add it's z1 plus z2, I just take x1 plus x2 and y1 plus y2, or I can do it in the polar form, as I'll show you in a minute. And that just gives me these terms, and that you can easily verify is this number over here. So if I then write it back as a complex number, which I can do by identifying that 1.5 is some new r prime cosine theta, and 0.866 is r prime sine theta, I can calculate r prime as just square root of this term plus this term squared. Okay, which is just the usual way to find when something is cosine and sines, you just calculate the squares and find the r prime. And similarly, to find the angle, I just take the tangent of or tan inverse of y over x. That gives me this complex number over here. Okay, so that's the equivalent polar representation of this complex number in this form. Okay, if you don't know how to do that, we can talk about it, or I can redo it again in the next class. Okay, so that gives me the real. If I take the real part of this, I'll indeed get back the answer that we had in the earlier class. I can also do this in the polar form, which makes it even more easy. So e to the I omega t and e to the I omega t, e to the I pi over 3. And now I add them up. I get this, again, this e to the I omega t is common, and then I get 1 plus e to the I pi over 3. And to calculate, say, the magnitude of this complex number, I just take z times z star, which will give me these terms, 1 plus e to the I pi over 3 times 1 plus e to the minus I pi over 3. So that gives me 1 plus 1 plus e to the I pi over 3 plus e to the minus I pi over 3, which is 2 cosine pi over 3. And that, again, if I verify that, it's equivalent to the wave psi that we got from that earlier expression. Okay, I'll stop here and we'll continue in the next class.